Yesterday we had a little demonstration where we saw the effect of different amounts of light and different types of light on the emission of electrons from a metal surface. The photoelectric effect was discovered in 1887 by Heinrich Hertz. The photoelectric effect says essentially this: when light strikes metal, or sometimes other materials as well, an electron or electrons are sometimes ejected. For 18 years following Hertz's discovery, nobody could figure out how to explain the observations that were made. It was observed that the type of light affected the emission of electrons, not the amount of light. Classical theory would predict the amount of light would affect the emission of electrons, but that didn't agree with the observations that were made. Now we enter Einstein, 1905. Einstein came up with this theory that we call photon theory. Photon theory says basically this: light exists not only as a wave. We're not discounting that now. We still have diffraction, interference, refraction, polarization to support the wave theory of light. But now we also have the particle theory of light. Light exists not only as a wave, but also as a particle. That particle of light is called a photon. We define a photon technically as a quantum of energy. That's an important definition going forward over the next week. A quantum of energy. We think of a photon as a particle of light, but its real definition is a quantum of energy. Now, how did that explain this photoelectric effect? How did that explain why the type of light would affect the emission of electrons rather than the amount of light? Well, because the equation that Einstein used to describe a photon of light says this: E is equal to h times F. E stands for the energy of the photon. And we're going to wait a second to tell you what the units for the energy of the photon are. You'll see why in a second. The energy of the photon. F stands for the frequency of the photon. You can see here that we're not eliminating this whole wave theory of EMR. If we're talking about a particle of light with a frequency, like frequency is a wave term, right? This is a wave-particle duality thing. In fact, if you look at the back wall there under physics principles, principle 9 is wave-particle duality. The first equation you see under that is E is equal to h times F. If you use this equation, you've used wave-particle duality. It's in itself telling us that we have a particle of light with a wave nature. It also tells us that the energy of that light is related to the frequency. That's why Hertz and his contemporaries observed that it was the type of light that affected emission rather than the amount of light, because the energy is related to the frequency or the type of light rather than the amount of light. Now, what is this? By the way, the units for that would be Hertz, right? What does this H thing stand for? This H thing stands for a constant that we call Planck's constant. Max Planck was a guy that came before Einstein. He was the first guy to really introduce quantum theory. Okay, he didn't give us photon theory or an explanation of the photoelectric effect, but he introduced the idea of quantum theory, the idea that energy is quantized, the idea that we can have discrete values of energy only. You can have this many joules, or twice that, or 3 times that, but nothing in between. Okay? But that's why he's got a constant named after him, right? Because he was the first guy to really start this stuff. But it was Einstein that extended it to the concept of light and photons and particles, wave-particle duality, and so on. Now, what's the value of Planck's constant? Well, there's 2 values, actually, which is kind of weird. The first value is 6.63 times 10 to the negative 34 joules seconds. Joules, not joules per second, joules times seconds. 6.63 times 10 to the negative 34 joules seconds. Not going to remember that number? That's okay. It's on your data sheet. So is the other one. The other one that says 4.14 times 10 to the negative 15 EV times seconds. What's an EV? Electron volt, right. Now, how can we have 2 different values for a constant? How is that possible? Like a constant is a constant, right? Isn't it always supposed to have the same value? We look at the gravitational constant from physics 20, 6.67 times 10 to the minus 11. That's what it always is. We look at Coulomb's constant, 8.99 times 10 to the 9. That's what it always is. How can we have two different values here? Yeah, we don't really, right? The speed limit on the highway is 100 kilometers per hour. Well, it's also 62 miles per hour. It's the same thing. It's just two different units that describe that, right? So it's okay to have two different values. It depends on what units you want to use. Now, what units are we going to use for the energy of a photon? Having said that, well, it depends. Sometimes we might use joules. Sometimes we might use, what's the other one? Yeah. Which one are you using? Well, it depends on which value of Planck's constant you use. If you used 6.63, then you're going to get an answer in joules. If you used 4.14, then we're going to get a value in electron volts. Most times, you can use whatever unit you want, unless it specifies an answer in joules or in electron volts, right? Most times, you can use whatever happens to be convenient for you. There are a few times when you can't. There are a few situations where you need to use joules. So here's what I'm going to say. For the time being, if you want to use either one, go ahead, use either one. I'll point out those situations when we encounter them where you must use joules. But if you think you might get confused about that, like we've got to use joules sometimes, but sometimes we can use whatever we want, you can, if you want, always use joules. Even if an answer is in electron volts, you can use joules through the question. Okay, use yellow through the question, and then convert to electron volts at the end. Okay, using joules always works. Using electron volts usually works. Okay, I'll point out when it doesn't. Okay, but again, if you think you might get confused by that, and you want to go with what always works, then just use joules. Okay, it ends up being a little bit more work sometimes because there's an extra conversion in there, but it always works for us. Okay, we're going to do a couple quick questions on photons, and then we're going to go and talk a little bit more detail about the photoelectric effect, which is what Einstein used this theory to explain. The whole thing that Einstein got the Nobel Prize for. Example number 1, on your example question handout says, determine the energy of a photon that has this frequency. Well, this is a pretty easy question, right? The energy of this photon is h times f. Now, what value of Planck's constant do you want to use? 6.63 or 4.14? Does it matter? No, not unless it specifies what you want your energy to be measured in. This doesn't, so we can use 6.63 or 4.14. I'm going to use the 6.63 value. 6.63 times 10 to the negative 34 joules seconds times the frequency, which is 5.0 times 10 to the 14 hertz. When we multiply those two numbers together, we get a value of 3.3 times 10 to the negative 19 joules. Now, if this was a multiple choice question or a numeric response question where you were specifically asked for the answer for energy in electron volts rather than joules, you would have two options. You could have used the 4.14 value and gotten electron volts right off the top. Or you could do what we just did and then convert it to electron volts from joules. Remember that? You've done that quite a few times now. You just say 1 EV is 1.6 times 10 to the minus 19 joules equals X EV over 3.3 times 10 to the negative 19 joules. So either method there would work. I'm just going to leave it as 3.3 times 10 to the minus 19 because it didn't specify here. But if it specified joules or electron volts, then you'd have to watch for that. Let's take a look at our second one now. Example number 2 says, how many photons? Oh, how many photons? Looking for a number of photons. Okay, a frequency 1.00 times 10 to the 16 hertz would it take to obtain a total energy of 2.5 times 10 to the 22 joules? A number of photons. Any idea how we might find a number of photons? Yeah. Yes. Yeah, remember what we did for the number of electrons. We divided the total charge by the charge of one electron. Okay, if we want to find the number of photons, let's divide the total energy divided by the energy of one photon. Now, the total energy is given to me here is 2.5 times 10 to the 22 joules. What's the energy of one photon? Well, we just learned how to find that, right? E is equal to h times f. Since the top is in joules, let's use joules on the bottom as well. 6.63 times 10 to the minus 34 joule seconds times a frequency of 1 times 10 to the 16 hertz gives us an energy here of 6.63 times 10 to the negative 18 joules. So let's sub that in here. That gives us a value of 3.8 times 10 to the 39. There are no units associated with that because the units cancel, right? Joules over joules gives me nothing. Now let's spend a little bit more time talking about this phenomenon that photon theory correctly explained. You got to understand how this kind of transpired. Einstein comes up with this photon theory. Nobody else could explain the photoelectric effect. Einstein comes along and says, look, I got this photon theory. It explains the photoelectric effect beautifully. If I explain this photon theory, and if it explains the observations that nobody else can explain, will you believe me? Will you believe that this photon theory actually is correct? People basically said, yeah, okay, we'll buy that. And that's what happened. So Einstein explains the photoelectric effect. The observations that were made agree beautifully with photon theory. And that hadn't happened before with any other theory, any other classical theory. So this photoelectric effect that Einstein is given so much credit for explaining really was just his evidence to support his particle theory of light. So now we've got four properties of waves that are exhibited by EMR: refraction, diffraction, interference, polarization, that support the wave theory of light. But we've got one more thing now that supports the particle theory of light, and that is the photoelectric effect. So if you ever ask for evidence to support the particle theory, one of the answers is the photoelectric effect. We'll talk about the other one in the next couple of days. The photoelectric effect, again, discovered in 1887 by Hertz, explained by Einstein in 1905 with his photon theory. Light strikes a metal, an electron or electrons, sometimes one, sometimes more, are ejected sometimes, not always. Depends upon, well, as we know now, the frequency, because the frequency is related to the energy. Even Hertz said it depends upon the energy, but Hertz's idea of where the energy came from was wrong. Hertz said the energy came from having more photons. Not having more photons, because he didn't have that term, but having more light, having brighter light, more intense light. But that didn't work. Having a different kind of light worked. He just didn't know why, until Einstein said the type of light is related to the energy rather than the amount of light. So here's Einstein's explanation. Light is a particle whose energy is related to the frequency. This is the most important part of this. This is the most important part of this whole deal, that the energy of the light is related to the frequency. By the way, it's also related to the wavelength, right? Einstein said that E is equal to H times F, but F is equal to C over lambda, so we could say H times F is equal to HC over lambda. In fact, that's the way that equation actually appears on your data sheet, both forms of it, HF, HC over lambda, same thing. That means higher frequency of EMR gives you higher energy, and higher energy makes it more likely that electrons will be ejected, or in other words, that photoemission will occur. If the frequency is related to the energy, and you need a certain amount of energy in order to cause electrons to be ejected, there must be a minimum frequency at which electrons are ejected. Right? You have light that is below this frequency, it's below the energy that's required, and nothing's going to happen. If you have light that's above this frequency, it's going to be above the energy, and something's going to happen. Electron or electrons are going to be ejected. That frequency above which electrons will be ejected, below which electrons won't be ejected, is called the threshold frequency. The symbol for threshold frequency is F0. It is the minimum EMR frequency necessary to eject electrons. In other words, if the frequency of EMR is above the threshold frequency, electrons are ejected. If the frequency of EMR is below the threshold frequency, electrons will not be ejected. Does that make sense? Why? Well, because frequency is related to energy. You need to be above a certain amount of energy. Therefore, you need to be above a certain amount of wavelength. Now, just as a little aside, wavelength kind of goes with that as well. Threshold frequency is usually the term that we use, but we could use a term threshold wavelength. The threshold wavelength, however, wouldn't be the minimum wavelength necessary to eject electrons. The minimum wavelength there, that is. It would be the maximum wavelength, right? Because wavelength and frequency are inversely related to each other. So I'm going to say over here in brackets, lambda max would be the threshold wavelength. If you have a wavelength that is below the maximum or the threshold wavelength, electrons are ejected. Okay, if you have a wavelength that is above the threshold frequency, or wavelength I should say, electrons will not be ejected. Make sense? You gotta have a certain amount of energy. In order to have that energy, you need to be above a certain frequency, or you need to be below a certain wavelength. Same deal, really. Of course, threshold frequency, the minimum frequency necessary, is going to correspond to a minimum energy necessary. That minimum energy necessary is called the work function. The symbol for the work function is a capital W. It's the minimum EMR energy necessary to eject an electron. In other words, if your energy is above the work function, electrons are ejected. If your energy is below the work function, electrons are not ejected. Energy is related to frequency, right? So if you're above a certain frequency, you're going to be above a certain energy. You're going to be above the work function. Now, by the way, the minimum energy necessary to eject an electron, why is it the minimum energy necessary to eject the electron? Well, because there's a certain amount of energy that gets used up in the process. That corresponds to the work function as well. So you could say it's the minimum energy necessary to eject the electron, but you could also say it's the energy used up in the process of ejecting an electron. Slurpees cost about $2. Okay, if I go to 7-Eleven, the minimum money necessary to buy a Slurpee is $2. Why? Well, because I use up $2 in the process of buying a Slurpee. The minimum energy necessary to eject an electron is the work function. Why? Well, because the energy that's used up in the process of ejecting an electron is the work function. Let's give you another equation now. We already have this one boxed off in blue up here, right? Energy is HF or HC over lambda. We've used that, and you guys are okay with that, I think. Energy is HF or HC over lambda. If energy is HF, then minimum energy, or work function, is H times, what comes next? Minimum frequency, right? Energy is H times frequency. Minimum energy is H times minimum frequency, H times F0. This is on your data sheet. This is not on your data sheet. But of course, it's the same thing, right? If energy is HF or HC over lambda, then work function is H times threshold frequency equals HC over threshold wavelength. Just that second part of it doesn't appear on your data sheet, that's all. You can use it, but you'd have to either remember it or kind of figure it out. Now, clearly, we've already established this. You can write down what you need to write down or not write down what you don't need to write down of this if you've already taken some notes on this, whatever you need to do. If your photons are below the threshold frequency, no electrons will be ejected, right? We said if F is less than F0, nothing happens, right? We've already established that, right? Photons above the threshold frequency will cause electrons to be ejected. So if F is greater than F0, it's a check mark. Electrons will be ejected. If this is the case, right here, then it will be a 1-to-1 ratio. In other words, if you're below the threshold frequency, there is no ratio because nothing happens. The electrons aren't ejected. But if you're above the threshold frequency, it's a 1-to-1 ratio for electrons to photons. So one photon above the threshold frequency will cause one electron to be ejected. 27 photons above the threshold frequency will cause 27 electrons to be ejected. And assuming electrons are ejected, if the frequency is above the threshold frequency, okay, if this happens and electrons are ejected, then a higher frequency makes the electrons more energetic. Why? Well, because the energy, remember, of the photon is related to the frequency. If you have a more energetic photon, then the electron that's released is going to be more energetic. But be careful. Higher frequency above the threshold frequency means more energetic. More photons, or in other words, more light. More photons could be brighter light, or it could be light shining on the surface for a longer time, either one. Right? It's more light, more photons, more light, if you're above the threshold frequency, will cause more electrons to be ejected. And that comes back to this, right? 1-to-1 ratio of photons to electrons. You're above the threshold frequency, you jack up the frequency even more, still got one photon, still got one electron, but a more energetic electron. But you increase the number of photons, increase the brightness, the intensity of the light, more photons will cause more electrons because it's a 1-to-1 ratio. One photon causes one electron. If you increase both, the frequency and the number of photons, then you get more electrons ejected with more energy, more energetic electrons. Okay. There's two terms, well, one term here really, that's going to derive for us an equation, and another thing that's going to derive for us an equation as well. Once an electron has been ejected, we sometimes apply a potential difference to stop that electron dead in its tracks. Now, the reason we might do that, and you'll see tomorrow or the next day, depending upon which day we do it, the reason that we may do that is to determine some of the properties of the metal. Each metal has a different threshold frequency. Maybe we're studying metal X and we want to determine its work function or its threshold frequency. In order to do that, we do an experiment where we stop the electron once it's been ejected. That electron, when it was ejected, had a kinetic energy of 1/2 mv squared, right? If you're stopping an electron, that's like a car going up a hill where kinetic energy is converted to potential energy. So we would say kinetic energy of the electron once it's been ejected ends up being equal to potential energy of the electron once it's been stopped. So we're going to say the kinetic energy, it's actually the maximum kinetic energy of the electron is equal to 1/2 mv squared, or mv maximum squared, is equal to QV stop. The stopping potential, electric potential that's required to stop the electron. That's not the photoelectric effect itself, because the electron's already been ejected, but it helps us to determine some of the properties of the metal within the photoelectric effect. Now, I'm just going to kind of rewrite this over here. just in a different order. It doesn't matter really what order you list it in. I'm just doing it in this order because what's boxed off there is what appears on your data sheet. But you already know that dk is equal to 1/2 mv squared, right? The reason I did it in this order was just to logically lead you to the equation, but that's not the way that it appears on your data sheet. Finally, one last thing, and then we'll wrap it up for the day here. The law of conservation of energy kind of ties all this together. Law of conservation of energy says that like what you start with is what you finish with, right? The energy that we start with here is what? What is it in this whole thing that has the energy in the beginning? Photon, light. God said, let there be light. And there was light. Okay, the photon has an energy of h times f. That's the initial energy. The final energy is, what is it that has the final energy? The electron. It's the kinetic energy of the electron, or really the maximum kinetic energy of the electron. But wait a second, there was energy used up in the process. So the final energy doesn't actually equal the initial. The initial equals the final plus whatever we used up in the process, which is the work function. Now, I'm going to start this because it's an important equation, and it does not appear on our data sheet. We're going to use this equation often, but yet it doesn't appear on our data sheet. I think the reason they left it off is because they want you to derive it from conservation of energy like we just did.